Hello. So we are now doing homework number five, number one. Professor Chen has graciously given us sort of a write up of what I'm about to explain, but still need to explain it. And I'm going to translate it, bring it over here. If you have something of the sort z equals to x plus y, how do you find big F of z, and how do you find little f of z? And there's two ways you can do it. All right, so here I have y, any variable y equal to negative x plus z. Basically, it's just like, it's the same thing. It's the same equals, like z equals to x plus y. I'm just basically switching around the variables. Big F of z equals to negative infinity to a double integral from negative infinity to infinity, and negative infinity to negative x plus z, because, as you can see, negative x plus z cannot be greater. It can only be less than or equal to y in order for this double integral to work, because as you can see, dy is the inside integral and not the outside integral. And so our outside integral d of x, and the outside bounds are negative infinity to infinity. To find little f of z, we need to take the derivative of big F of z, right? So basically, but this is just a translated form. It's very ugly, but it's a translated form of big F of z, the derivative of big F of z. And we use a fundamental theorem of calculus to get to the integral of negative infinity to infinity of f of x, y, x comma z minus x, which is another way of saying y, dx. Same thing over here. We're just going to, instead of, so over here we had y equals to negative x plus z. Over here we have x equals to negative y plus z, or x equals to z minus y. Same thing, we have big F of z equaling to the double integral from negative infinity to infinity dy, I don't really know how to say this double. So the inside integral is negative infinity to negative y plus z. Again, negative y plus z can only be less than or equal to x, okay? Otherwise, the integral will not work. And the inside integral is dx. As you can see over here, it's dy. Over here, it's dx, because your bound is in terms of y. And the outside integral is negative infinity to infinity. The integral of that dy, yeah, of x, f of x, y, x comma y. Little f of x, again, same thing. You take the derivative of big F of z in order to find little f of z. And here is, again, the translated form of the derivative of big F of z, and using the fundamental theorem of calculus, we arrive at the integral of negative infinity to infinity f of little f of z minus y comma y dy. And it's a good thing to note that if x and y are independent, which I think is implied in this explanation, f of x comma y is actually equal to f of x times f of y. So we can use that to our advantage, because over here, f of x comma z minus x is actually f of x times f of x times f of y z minus x dx. It's the convolution of f of z in the y plane and f of z in the x plane. Same thing over here. If x and y are independent, we have, here's what we got to from the fundamental theorem of calculus, from negative infinity to infinity, f of z minus y comma y dy. Again, we can, if they're independent, we can multiply them. So that's what we're doing, as you can see here. And that's the convolution of f of z in the x plane and f of z in the y plane. Okay, so, but we need to move on to the second explanation, which is, again, we have our z equals to x plus y over here. If so basically, a lot of translating over here. Big F of z equals a probability of any variable z less than or equal to z, equals to the probability of any variable x plus y less than or equal to z, equals to the big F of x plus y, basically big F of z. We turn this into the integration of two random variables. F of x plus y equals to the integral of x plus y less than or equal to z, f of x comma y. Basically, I showed you the methods before, but here are the graphs. Over here, we want to find this area, and over here, we want to find that area. Z is some constant in both graphs, but this is the y-axis is vertical, and over here, the x-axis is vertical, and that's how kind of like those are the graphs of what we are looking for. Okay, so those are the two methods. I call it method 1A and method 1B. Sorry, that's just 2B, but it should actually be a 1 because they're both like derivatives of the same method, so I want to make that clear. So over here, so method 1B, okay? So now I'm going to go on to another method, and we'll call it method 2, which is a step function method, okay? Let's go back to basics. Big F of z equals to, this is the problem that we're presented with. Double integral of x plus y is any variable x plus any variable y is less than or equal to z. F of x comma y dx dy. We're going to translate that to negative infinity to infinity, negative infinity to infinity. The double integral of f of x comma y, sub function of z minus x plus y, dx dy. And over here we can write this because we know that any variable of x plus any variable y must be less than or equal to z. The sum function definitely is 1 in this case for any variable x plus any variable y less than or equal to z. If any variable x plus any variable y equals to z, then the integral is just 0, and this whole, because if the step function is 0, this whole integral is 0, so that doesn't really work. On to method 2. Okay, here we have method 2a. We actually take that and we put parentheses around z minus x. So over here, we have a stipulation that y cannot be greater than or equal to z minus x, right? Because then the argument is negative and the step function becomes 0. So as you can see, that double derivative over here translates to this derivative because that step function goes to 1. But the upper bound is actually from the inside integral from negative infinity to z minus x f of x comma y dy. The upper bound is actually z minus x because, like I said, z minus x, y cannot be more than z minus x, okay? Same thing over here. We're basically just switching around the parentheses. Instead of z minus x, we're doing z minus y. X cannot be greater than z minus y. X must be less than or equal to z minus y. Otherwise, same thing, the argument is negative and the step function is 0, thus ruining the integral. Okay, so you take the negative, so the upper bounds, basically z minus y, and basically that's what you set your upper bounds because x cannot be more than that. It can only be equal but not be more than that. And that's the translated function of that. So what we wanted to show here in this step function method was that the step function method really comes out to the same conclusion as, sorry, it says method 3, but I'm going to change that to method 2.